morning, students.
Good morning, sir.
So we'll start with the lecture, today's lecture. In the topic on electromagnetic theory 2, which is the magnetostatics. In the chapter 1, we had started with Biot-Savart's law, and we had arrived at the formula for magnetic field due to wire in any shape. Then yesterday we had applied that Biot-Savart's law to the straight wire carrying current, and we had found the formula. Today we will apply Biot-Savart's law to find the magnetic field at an axial point of circular coil of a wire. See, when you say coil, there are many turns. So we have a loop. Loop means it is a single turn like this, carrying a current. It is carrying a current. It is a single loop. A coil means there are many loops, winding is there, and when a current is flowing, it will flow in the same sense through each loop. If it is clockwise, in all the loop it will be clockwise. If it is anti-clockwise, in all the loop it will be anti-clockwise. So direction of magnetic field produced by such current will be same. So we can add the magnetic field produced by each and every loop to get the magnetic field produced by the coil. Then when we say coil, see coil is there like this. This is a coil. Then if you draw the line perpendicular to the plane of the loop, passing through the center, now that line is called as the axis. This is the axis. So this is the axis. It is the axis. Now we are going to find magnetic field at any point on the axis. At any point, at a certain distance from the center, we will find in general the magnetic field at any point on this axis of the coil, and then we can get magnetic field at the center by saying that the distance x is equal to 0. So first we will find in general axial point of the circular coil of the wire, and from that we get it what is the magnetic field at the center, and that is in fact normally it is required. Most of the cases what is required is a magnetic field at the center. In the rare cases you require the magnetic field at any point on the axis. Now we have drawn here diagram. So this is the coil we have drawn. It is carrying a current. So it is carrying a current. We mark the current like this. The current is flowing. See, this is the current. Current is flowing because it is connected to the battery. But this is only representation. It is not a circle. It is not a circle. In fact, what happened is this is connected. This is. Can all of you hear me? Hello?
Yes, sir.
Okay. Some may not be able to hear it. Maybe it is their problem. Okay. I'll continue. So now there is a current. Okay. So this is only representation. Then what we have done here is in this diagram. See, in this diagram, what we have done is we have drawn this loop, or we have drawn this coil in xy plane. See, this is x-axis, this is y-axis, and this is z-axis. See, this x, y, z you can draw this way also, because normally what happened, where I have shown here y is x, where I have shown it is z is y, and what is shown x here, normally it is a z. But what happened is that coordinate system can be rotated. In fact, when you rotate it, what you will get is like this. So here x y plane is horizontal, z-axis is vertical. So this coil is in xy plane. It is of the radius a. So coil is of it is of this radius a. Then we are finding the magnetic field at a point P on the axis. It is now z-axis turns out to be the axis of this coil. See, what is the meaning of axis of the coil? To this loop, drop a perpendicular passing the center. This is a center. See, this is the center, and the line passing perpendicular, passing the center, is the axis. So now here, axis of the coil coincide with the z-axis, and the coil is of the radius a, and the point P where you are finding the magnetic field is at distance z. We are using the symbol z. You can use also any other symbol. I am using the symbol given in your prescribed textbook, the Ries and Milford. Okay. Now to find a magnetic field, we can using Biot-Savart's law, we can find magnetic field due to the element. So now on this loop, we choose the element like this. Is the element. It is the element. Length element it is. Length element means its length is tending to 0, very small. We call it the dl, and we give it as a vector quantity. We draw the tangent, and the tangent is the direction of the that element, and the direction is according to the current. See, the current is flowing like this. That's why direction of dl. See, this is the direction of that dl. Okay, that is as per the current. Now this is subtending the angle d theta, small angle, because element is small, angle subtended is small. Then from the y-axis, this radius, the element is making angle theta with the y-axis. See, this radius vector making angle theta. See, this is the angle theta. See, this is the angle theta. That is the angle theta, and this is the angle d theta. Then, as per our notation used in the Biot-Savart's law, that the distance of the element from the origin, so now origin is here, distance of the element from the origin is vector r1. This is a position vector of element is vector r1, and position vector of the point where you are finding, see this point where you are finding the magnetic field is vector r2. So see, vector r1 is the position vector of the element, and vector r2 is the position vector of the point where you are finding the magnetic field. So this position vector is with respect to the origin. Now beside that, we call this distance as z. Now this z is a constant, a given point, z is constant. Now this dl can be any part of that loop. Now we have stated this. Yesterday we have used this one, equation 1. We have stated it 2 days before. The expression for magnetic field is mu naught I divided by 4 pi integral vector dl cross vector r2 minus vector r1 divided by vector r2 minus vector r1 cube. So this is the expression for the Biot-Savart's law. Now we have to write here this equation 1 in terms of the symbol which we have used in this diagram, that is for the coil. Okay. Now what we have to find here is what is vector dl in this case, and what is vector r2 minus vector r1. Now first of all, see, this is dl is like an arc. Length of the arc is s equal to r theta. So s equal to r theta. This s is dl, and this dl equal to r means a, radius, and theta is at angle d theta. So this is there. This is a magnitude. A d theta is a magnitude. Vector dl equal to a d theta is a magnitude. Then this direction, see this direction of vector dl. See this direction of vector dl. So we have to multiply some unit vector to unit vector in the direction of vector dl, and it is written here. See, it is written here minus I cap sin theta plus j cap cos theta. Okay. Now this part I am not deriving it. It will turn into another half page. It is not expected from you. Even this Regent Milford, this book directly give this formula. Okay. So if you know the polar coordinates, then you can easily write this. Okay. It is taken to be a standard. The polar, these are polar coordinates, r and theta. Polar coordinates. In polar coordinate, actually there is a standard way for this. Okay. So this I will not derive it. Okay. Very few Indian textbook they give about this, but it is little about how the page derivation, how you get the unit vector in the direction of this vector dl. Okay, so you have to remember this minus I cap sin theta plus j cap cos theta. Okay, then vector r2 minus vector r1. See vector r2, that means this one. This is vector r1 minus vector r1. Again, this also another small derivation is there. So this is not expected from you as per your prescribed textbook. So again, this one you have to remember: minus I cap a cos theta minus j cap a sin theta plus k z. Okay, so this is what is called as a polar coordinate. In fact, this is the standard equations in the polar coordinate. Okay, so we are not going to derive it. Then once you know this, see vector dl is a theta minus I cap sin theta plus j cos theta. Magnitude is a d theta. Okay. Then vector r2 minus vector r1 is minus I a cos theta minus j a sin theta plus kz. Now to find the magnitude of this, see to find the magnitude of this. Now this, say, it is just like magnitude of xi cap plus yj cap plus zk cap. Magnitude of that is square root of x square plus y square plus z square. So in this case here, this multiple of I cap, see multiple of I cap is minus a cos theta. So minus a cos theta square. Then multiple of j cap is multiple of this j cap is minus a sin theta. So minus a sin theta square plus multiple of k cap is z. So z square and root of that. Because this for position vector, actually it is xi cap plus yj cap plus zk cap. The magnitude of the position vector is square root of x square plus y square plus z square. Okay, that is how we have written it here. So this we use our previous knowledge how to get the magnitude of the position vector. Then this one is a square cos square theta. Then this term is a square sin square theta. You take a square common. If you take here a square and this a square common, what remains inside is cos square theta plus sin square theta, which is 1. So this term turns out to be a square. It turns out to be a square. Because a square you take it out, what remains inside is cos square theta plus sin square theta, which is 1. So now this bracket turns out to be a square plus z square. Beside it, raised to half is there. So modulus of vector r2 minus vector r1 equal to a square plus z square raised to half. And that is what we want. We want what is vector r2 minus vector r1, what is modulus of vector r2 minus vector r1, and what is dl. So now all these things we have to substitute in this equation 1. So this is the equation 1. So this is the equation 1. And we have found it what is dl, what is vector r2 minus vector r1, what is modulus of vector r2 minus vector r1. You substitute it here. This equation vector dl, vector r2 minus vector r1, where modulus of vector r2 minus r1 you substitute in the equation 1 and this substituted here. Say this dl, a d theta I have written here, a d theta I have written here, and this part, say this part I have written it here in this bracket. Cross product is there. Vector r2 minus r1. So this we are substituting here. Divided by modulus of r2 minus r1 cube. So modulus of vector r2 minus vector r1 is a square plus z square raised to half. Cube means raised to 3 by 2. So this is what we get. Raised to 3 by 2. Then you open this bracket. Say there are two brackets. They are multiplied with the cross product because their vector quantities are there. you take a first term into second bracket, second term of the first bracket into second bracket. So what you have taken here, minus I sine theta into the second bracket plus j cos theta into the second bracket. So this is what we have done it here. Then next what is done is this a, see the limit is from 0 to 2 pi. See, limit is from 0 to 2 pi because this theta, see, you have to this theta, you start from here, element is here, you have to go on choosing the element like this and you have to do it for one round like this. One round means 360 degrees, that means the 2 pi radians. Okay, so you are adding this, the magnetic field due to the dl for an angle from 0 to 360 degrees. 360 degrees means 2 pi radians. So that's why limit is from 0 to 2 pi. Limit is from 0 to 2 pi. Okay. Then this a is taken outside. Then this one, see this one is also taken outside. It is taken outside like this. Okay. So a is taken outside and a square plus z square raised to 3 by 2 is taken outside. Then here we try to take a cross product. See, minus is plus, vector I cap plus vector I cap, cross vector I cap. See, a cross a, that is 0 because magnitude is ab sin theta, theta is 0, sin 0 is 0. Magnitude is 0 means vector is 0 vector. So that's why minus I cap sin theta minus I a is cos theta. This I cap cross I cap is 0. So that's why this first term becomes 0. Then second term, see minus plus I cross j. This I cross j is k. We written here k and sin theta and a sin theta. See, this is a sin theta and a sin theta is a sin square theta. Minus plus, this minus and this minus plus, then I cross j is k. So unit vector k, a sin square theta. So this we have evaluated the first bracket. Second bracket, j cos theta minus a cos theta. So now here, this cos theta into a cos theta. See, the cos theta into a cos theta is a cos square theta. See, here I am coming. A cos square theta. Then plus into minus is minus. Then j, see I cross j is k. See, I cross j equal to k. So j cross I is equal to minus k. So minus plus. So you get plus k cap. A cos square theta. So what we have done here is plus into minus. J cross I is minus k. So minus plus. So plus k cap. This cos theta into a cos theta, that is a cos square theta. Then next term, j cos theta. See this term and this term. J cos theta into minus j a sin theta. See, j cross j is 0. So that's why it is 0. This is 0. Then third term, when you take this inside, j cos theta plus kz. So z cos theta, it will be z cos theta. Then j cross k is plus I. So we get like this. And that what is there is d theta is there. This d theta is there. So we have written it here. Then next, you take this term and this term. Take these two terms. Ka sin square theta plus Ka cos square theta. So Ka comes outside. Sin square theta plus cos square theta is 1. So what remains there is Ka. Then j sin theta z plus I cos theta z and d theta. So now this we have found. See, this equation we have found in the previous slide. Then integrate. See, integrate. So when you integrate Ka d theta, k is constant. See, k is constant. So integral of d theta is theta. See, integral of d theta is theta. So that's what we get. See, when you integrate this, Ka d theta, Ka is constant, integral of d theta is theta. Then integral of sine theta or integral of cos theta, see over 0 to 2 pi, these are over full cycle, if you integrate, you will get a 0. So we will not bother to integrate it. Even if you integrate it, integral of sine theta will be minus cos theta. When you substitute the limit 2 pi and 0, the resultant will be 0. So this will be 0 and this will be also 0. Then substitute for theta. Theta is a variable, upper limit. See, Ka I have taken outside. So when K is taken outside, K cap here, A into A is A square. And substitute the upper limit for theta, 2 pi. Substitute the lower limit for theta, which is 0. So it is into 2 pi. Then this 2 pi and this 2 pi will cancel. What remains there is 2. So what do you get? Mu naught I A square K cap divided by 2 A square plus Z square raised to 3 by 2. Then if you use the if you find out the direction of vector dl cross vector r, you will get it using a right hand thumb rule, because using Biot-Savart's law. Using Biot-Savart's law to find out the direction of the magnetic field, you have to find out dl cross r. And if you find a dl cross r, it will be perpendicular to the plane of the loop, and that is along the z axis. So it is then directed along the z axis. Then I mentioned that, say, there are many loops. See, for a coil, there are many loops. The current will flow there in the same sense. That means in one loop, if it is in anti-clockwise direction, other loop it will be also anti-clockwise direction. If in one of the loop it is clockwise direction, in all other loop it will be also clockwise direction. So that's why what happens is, the direction of magnetic field produced by each and every element will be same. All will be along the z-axis. So you can, to find the total magnetic field due to all the loops, you multiply by n. So n is the number of turns. So it results into mu naught n I A square K cap divided by 2 A square plus Z square raised to 3 by 2. Then when you take a modulus of this magnitude, B equal to mu naught n I A square divided by 2 A square plus Z square raised to 3 by 2. Now this is the formula. Actually later on we will require it. See, this will require it afterwards in the case of the Helmholtz coil, which you have done for your practicals. So that theory is also there in this paper. So this formula on the axial point of the coil, we require this formula for a magnitude B equal to mu naught n I A square divided by 2 A square plus Z square raised to 3 by 2. Then suppose you take this point at here. See, the point is at distance Z. So if you take it at the center, like this, Z will be 0. See, if you take this point closer and closer to the center, Z will become 0. So if you put the Z equal to 0, then you will get a magnetic field at the center. So when you put Z equal to 0, the denominator becomes A square raised to 3 by 2, that is A cube. So it becomes the mu naught n I A square divided by 2A cube. A square and A square cancel. This 2 and cancel, remains 1 there. So mu naught Ni divided by 2A. Mu naught Ni divided by 2A. There is a magnetic field at the center of the coil. Okay, so now this is the formula. Actually, we require it. Very simple. Actually, both these expressions you already found in your 12th standard. But there you found the magnitude directly. Here derivation is as a vector. Okay, as a vector you have to find out do the derivation. Okay, so at the graduation level, because magnetic field is a vector, you have to do the derivation for the vector. In the 12th standard, you found the magnitude separately and you discuss about the direction separately. Then how to find a direction? See, you can find a direction by using Biot-Savart's law, but it becomes a little tedious to find a magnetic field using the Biot-Savart's law. So there are simple rules, mechanical rule to find a direction of magnetic field. So again we use the right hand thumb rule. Say, right hand thumb rule is there to find the cross product. Right hand thumb rule is there to find out the magnetic field due to the straight wire. right hand thumb rule is there to find the magnetic field due to the coil. Now, in the case of the straight wire, to use the right hand thumb rule, we hold the wire in our hand with thumb in the direction of the current and the fingers points in the direction of magnetic flux. And if you draw the tangent to that magnetic flux, what you get is the direction of magnetic field at that point. Now, in the case of the coil, what is to be done is you have to hold the thumb of the right hand perpendicular to the coil. See, as we have given here, see, this is the coil. See, the coil is in horizontal plane. Remember that the coil is in horizontal plane. We are considering this diagram. The coil is in the horizontal plane. So you keep your right hand thumb perpendicular to this plane of the coil. Now you can keep it perpendicular, either the thumb pointing upward or thumb pointing downward. Both are perpendicular. But you have to keep it in such a way that these four fingers are curled in the direction of the current. See, this is a coil. Current is flowing. You have to keep the fingers in the direction of the current. Then the thumb will point the direction of the magnetic field. That is how to get it. So here the direction of current is like this. So keep the fingers your right hand in the direction of the current. This is the current. Then the thumb will point the direction of magnetic field. Now in this case, the current is this way. So you have to, since the current is this way, you have to keep the fingers curling this way in the direction of current. If you keep the fingers like this in the direction of current, the thumb will point downward. So that is the direction of magnetic field. And here, basically what happened is, say, if you consider straight wire bent into the circle, actually for a straight wire, say for the straight wire carrying a current, these are the magnetic field lines. See, wire is vertical, magnetic field lines are circular in horizontal plane, concentric circles. So there will be concentric circles like this. Okay. So around that wire point, see the magnetic field lines forms a closed loop. This is the one difference between magnetic field lines and electric field lines. Electric field lines originate from the positive charge and terminates on the negative charge, whereas magnetic field lines from the closed loop. There is no positive or negative charge such as in the magnetism, because what happens is in electrostatic you can have only positive charges, you can have only negative charges. In magnetism you cannot have only north pole or only south pole. Whenever north pole is there, south pole will be also there. Whenever south pole is there, north pole is always there. So they come in as a pair. In fact, you take a bar magnet, cut it into two, again it will give the pair of the north and south. Again, if you cut it into two pieces, again it gives rise to north and south. So that is the reason that field lines from the closed loop. So there is no source as such for the magnetic field line. It does not originate or terminate, they form the closed loop. So basically for wire, the field lines are conscious. Even for this coil, the field lines will be like this. Around this wire, the field lines will be there like this. Around that. And concentric. Everywhere it will be there. In concentric circles will be there. Because magnetic field is there all around. Then look at this diagram which is given here. This diagram. I have shown the direction of current like this. Direction of the current in the clockwise direction. So now what is to be done is keep your fingers of the right hand in this direction. Fingers of the right hand in this direction. And then in that case, the thumb will point inside. So magnetic field in the perpendicular inside. Then in the second diagram, this diagram, direction of current is anti-clockwise. You keep the fingers curled in this direction. Then thumb will point outside. So this is the direction of the magnetic field. Okay. Now basically here what happens is the coil is behaving like a magnet. Coil is behaving like a magnet. And we know that when you consider a bar magnet, it is a north pole and it is a south pole. The field lines will come out of the North Pole and it will go inside the South Pole. It will be like this. The field lines will come out of the North Pole and it will go inside the uh, uh, South Pole, and it will circulate. It will circulate. It doesn't terminate, but from the closed loop. Okay, so the field lines are coming out of the North Pole and they are entering the South Pole. So as far as the coil is concerned, in this case, the field lines are going inside the coil. So now this part, this face of the coil, which you can see in the first diagram, the face which you can see is the South Pole. Other face of that coil is the North Pole. In this case, in the second diagram, the face of this which you see is the North Pole because this field is coming out. That means field lines are coming out. And other side of that coil is the magnetic South Pole. Okay, so even this loop is like a magnet. It is like a magnet. It is North Pole and the South Pole. It will produce a magnetic field. It will have the magnetic moment and so on. So this is what is so this is how to deal with the circular coil carrying a current. We can find the magnitude of the magnetic field as well as we can find out the direction. So with this, I'll stop here. Now today is Saturday. This coming week, you are having the practicals. Then I'll continue with this the week after the next. Okay. So at the same time, the timing will be same from Monday to Saturday. But coming week, you'll have the practical. So I'll stop here. Thank you very much.
Thank you, sir.
Okay.
Thank you, sir. Thank you.
Okay. Welcome.